All right, let us look at some excited levels. We are using this expression. For n equals 2, this is minus 0.5 divided by 4, this and 0.125. So that's some value here. Minus 0.125 Hartree. If you multiply it with this factor in EV, it will be minus 3.40. This is EV. Here we have a first excited level, n equals 2. Then for n equals 3, it is minus 0.0555 Hartree, or in EV, this is minus 1.51 EV. You see the difference between these neighboring levels, n equals 1 and n equals 2, is that minus that one. It's about 10.2 EV, this difference. But when you look at the difference between that level and that one, you see it is the difference between these two numbers. It's about 1.5 EV. So what's happening? As n goes higher and higher, level spacing gets smaller and smaller. In fact, when you go to very high energies, then for a very large value for n, this number approaches 0, isn't it? So there is a 0 here. So as energy goes higher and higher, the spacing between neighboring levels gets smaller and smaller, such that when n becomes infinite, the spacing between neighboring levels around that energy, around 0 energy, is extremely small. Of course, n equals 0, n equals infinity, which gives energy to be 0, corresponds to ionized electron. Electron is infinitely far away from the proton. Now let's go to the radial functions. So far we have discussed the results of solving this equation for the allowed energies, E. Now we are going to examine the radial functions. Please note that this differential equation contains L quantum number. But in the energy expression, you don't see any L. That's something important, that the energies are independent of the L quantum number. But we will see that the radial functions do depend on which value for L you use here. And the radial functions they depend on both the n quantum number, this quantum number, and also L. L must be smaller than n, so that allowed L values for a given n are L, it starts with 0, 1, 2, and its largest value is n minus 1. Please note that the energy level is fixed by n quantum numbers. So specifying n means specifying the energy level. For a given energy level, for a given n, the allowed values for L are only part of the possible L values. Lowest values, L values are integers starting with 0, but here the maximum value for a given n is n minus 1 for the L quantum number. Now, the n quantum number, because it determines the energy, it's called the principal quantum number. This quantum number L takes its name from its definition. L is related with the angular momentum. So the name of this quantum number is the angular momentum quantum number. Angular momentum quantum number. Now we may write the complete state function. The radial factor times spherical harmonic. The full state function is indexed by these three quantum numbers. Principal quantum number, n. Angular momentum quantum number, L, and there is this m quantum number. M quantum number is called the magnetic quantum number. But these are just names. So same indices are written as subscripts to the full function. So here, n, L, m. We had discussed in the rotation problem that the m quantum number here is a number between plus L and minus L. Therefore, for a given L value, m is restricted, m values. M values range from minus L to plus L. Now, in this problem, L values are also restricted with respect to the principal quantum number. In the sense that largest value for L is 1 less than n quantum number, n minus 1. All right, let us have some concrete examples about how many functions are available for each energy. Now, for if n is 1, which means the lowest energy, ground level, then how many possibilities are there for the L quantum number? Largest, L is restricted. The largest value is n minus 1. Therefore, what is, if n is 1, 1 minus 1 is 0. The only possibility for L is 0. Then, for this L, how many m values are available? Only 1, which is m equals 0, isn't it? So, number of functions with this energy, with minus 0.5 Hartree, n equals 1. How many? Only one possibility for this function. So let us Gn means number of functions for that n value. What do we call this in words? Degeneracy of the energy level. So for n equals 1, degeneracy is 1. What is another word for describing this situation? Is it degenerate or non-degenerate? Non-degenerate. Just two possibilities. Either there is it is degenerate or non-degenerate. And the definition is whenever number of state functions is more than 1, there is degeneracy. Fine. For n equals 2, L could be either 0 or 1, isn't it? Largest value is 2 minus 1, 1. Now, for this L, there is only one m value, but for this L equals 1, which m values are available? Minus 1, 0, and plus 1. Now, the functions are psi 1, 0, 0, which corresponds to this 2. 2, 0, 0, which corresponds to this selection. But there are also psi 2, 1, minus 1, psi 2, 1, 0, psi 2, 1, minus 1 functions. Therefore, how many? All of these functions are different functions. But all of them have the same energy. Hence, for n equals 2, this is minus 0.125 Hartree. Energy is the same, but we have how many different functions? 4 different functions. So degeneracy is 4. It turns out, when you count in this way, the number of different functions of this form for a given n. Remember, when you specify n, it means you have specified the energy. For a given n, the number of different functions is n squared. So for n equals 3, we will find 9. For n equals 4, we are going to obtain 16. 4 times 4. In general, this is how it continues. All right. I'll give you some explicit expressions for the radial factors so that you will have an idea about how they look like. These are available in the lecture notes. So n equals 1, 0. This is a normalization factor times e to the minus r. And the normalization factor, I will explain shortly how this number is obtained for n. For n equals 2, l equals 0, it is a normalization factor times 2 minus r times e to the minus r over 2. And here the normalization factor is 1 over 2 times square root of 2. For n equals 2, l equals 1, this is n times r times e to the minus r over 2. And the normalization factor is 1 over 2 square root of 6, etc. From these 3 examples for the radial functions, you see that all of them contain an exponential factor, e to the minus r. Here, this is e to the minus r over 2. In general, the general form of r and l is there is a factor which is e to the minus r divided by n times a polynomial in polynomial of degree n minus 1 in R. This is, look at the first one. N is 1 here. This is e to the minus r over 1, which is just r. And the polynomial is 0th degree. 0th degree polynomial means just a constant. In the second one, the exponential factor is e to the minus r over 2. It fits this. N is 2, so r over 2. It is multiplied with this polynomial, 2 minus r. The highest power here is r to the first power. And as we said here, n minus 1, for n equals 2, highest power is 1. This one also has r to the first power multiplied with e to the minus r over 2. But this is the general form. Please remember that r ranges from 0 to infinity. R is the polar variable. For r becoming infinite, the exponential factors kills all the polynomials, which means at r, when r becomes very large, all of these functions have 0 value because of the exponentials. Of course, r physically, what does it mean when we say r becomes infinite? The electron the distance of the electron from the nucleus is infinite. And this radial function becomes 0, which means probability of finding the electron at infinity far away from the nucleus is what? Remember, probability is related with square of psi. And psi is r times some angle dependent part, but we are just looking at the r part. If r becomes 0, square root also becomes 0, which means probability of finding the electron at infinity far away from the nucleus is 0. So what does it tell us about whether the electron is bound or unbound in such states? If there is no probability of finding the electron ionized, what does it mean? It is always bound to the nucleus. So these are bound states for the electron in the hydrogen atom. Remember that there are also unbound states in which the electron has been ionized. These results are describing only the bound states of the electron. Now, another property that you may see from these examples is that for r 0 to infinity, the first function has no zeros in this range. It's just e to the minus r. But the second function, you see, it becomes 0 at r equals 2. We are examining whether the function crosses the r-axis between 0 and infinity. We are not counting the origin. Of course, all of these functions become become 0 at infinity. In between, how many zeros there are? All right? We give it a name. We say number of nodes of the function. Number of nodes of a function is the number of zeros between 0 and infinity. So, for example, now this function has no nodes. No node means number of nodes is 0. Don't forget. This function has how many nodes? One node at r equals 2. This function has no nodes. Remember, we are not counting r equals 0. R equals 0 and r equals infinity are not included in counting number of nodes. Only in between. This function has no nodes. Now, it turns out, in general, number of nodes is n minus L minus 1. So that here n equals 1, L equals 0, 1 minus 1 is 0, 1 minus 0 is 1, but you subtract 1 more 1, you have 0. So there is no node, which means that function doesn't cross the r-axis. It doesn't become 0. This function, n is 2, L is 0, n minus L minus 1 is 1. So according to this rule, this function passes through just one node. So let me ask you, for instance, this function, R31, it corresponds to the radial function for 3 and L equals 1. This radial function has how many nodes? 3 minus 1 minus 1. It is one node, which means when you plot the graph of this function, R31, it will cross the R-axis just once. This function, R30, has how many nodes? It has 2 nodes, using that rule over there. In labeling our functions, both the radial function and the complete function, using 3 numbers there sometimes can be confusing. We may be confused about which one is n, which one is l, which one is m. Now, to give a solution to this problem, it is common to, instead of using numbers for integers for the L value, letters are employed. So L values 0, 1, 2, 3, and so on. A letter code is used. And the convention is L equals 0 is denoted by small s. L equals 1 with small p. L equals 2 with D. Now, from here on, in alphabetical order, except that J is omitted. The letters in the English alphabet, but F, G, H, I, 4, 5, 6, 4, 7, J is omitted. What's the letter after J? K. No J. In this is just a convention, all right? So, for instance, R31 is denoted as R3. This is L value. What is the letter code? P. One writes R3P. This way, it's easier to see which one is the principal quantum number and which one is the angular momentum quantum number. P is the angular momentum quantum number. Number 3 is the principal quantum number. In the complete function is also indicated by such symbols. So this is indicated as psi 2 s. The m quantum number is not needed to show here because s means L equals 0, and therefore there is just one m value, and m value is 0. So just this is written. On the other hand, for these functions, psi 2 L is 1, 2p. Now, the m quantum number is needed to show here. They are indicated by subscripts, p minus 1. This is psi 2p. What is m? M is 0. It is written as a subscript, psi 2p 0. And this one, psi 2p as subscript minus 1. So the m values are shown as subscripts for L larger than 0. This way, the information about the principal quantum number, angular momentum quantum number, and m value are indicated a little bit more clearly. Now, let us go into normalization of these radial functions. For simplicity in explaining this, I'm going to drop the subscripts like these. I will just use capital R. And the complete function is R times Y. This is in Y, I'm also not showing the quantum numbers L and M. Same with R. All of this for simplicity. The normalization condition is this. In this problem, how many independent variables are there? 3 independent variables. Therefore, this integral is how many dimensional? Triple integral. And integration limits are all space. Okay. The volume element let me call this part d tau 1 and this part d tau 2. And now we can write this expression. I'm substituting this expression here. Please note that all radial functions are real functions. There is no complex numbers in the definition of radial functions, as you have seen from the examples I have given, but all of the radial functions are real. Therefore, in this complex conjugate, it is just square here as far as R is concerned. Okay, now for the spherical harmonics, on the other hand, these are complex, could be complex valued, and most of them are complex valued. Therefore, complex conjugate is needed here. This is factorized. This integral is how many dimensional? How many variables are there here? Independent variables? Only one. So this is a one-dimensional integral over R. Limit for R is 0 to infinity. This part, this is how many dimensional? Y functions contain how many variables? 2. They depend on angles, remember? So this is a double integral here. But this part is just the normalization integral for spherical harmonics. The standard spherical harmonics, these functions, here I'm not showing the subscripts, they are normalized. That means the value of this integral for any one of the spherical harmonics is equal to, if I say these are normalized, what does it mean about the value of this integral? 1. Therefore, for the full function to be normalized, I can select the normalization constant in the R factor such that the value of this integral is also 1. Then 1 times 1. So this is my definition of d tau 1. This is the normalization condition for the radial functions. Because when this integral is 1, it is 1 times 1 is equal to 1. Therefore, the full function is normalized. Let us have a very simple example. Psi 1s was a normalization constant times e to the minus r. I had given this function before. Now, let us fix the value of n using this condition. We have n squared e to the minus 2r, 0 to infinity, r squared dr equals 1. The value of this integral is 2 over 8. This is a standard integral. So n squared is 4, which means if I take n equals 2 and write 2 times e to the minus r, this function will satisfy this condition with that n value. So it will be normalized. All right? Okay. Now, let us go back to this expression. This is our general expression for the probability of finding the particle. In this case, what is the particle in our problem? What is the name of the particle? Aren't you aware of what we are discussing? We have the electron in the hydrogen atom. So the particle is the electron. Applying the general concept to the electron in the hydrogen atom, this expression gives the probability of finding the electron in a tiny volume element, d tau. Now, let's write this more explicitly using the form of it. This is r square times y d tau 1 times d tau 2. Remember, d tau 1 contains only r variables. D tau 2 contains two angle variables. One is theta, the other is phi. Now the question is this. Imagine a sphere with a radius r. So the cross section will be like this. Imagine another sphere which is concentric with this one. And the difference between the radius of the outer sphere and the inner sphere is dr, delta r. Remember, delta r is a very small number. And you should imagine this as a sphere. This is just a cross section. Now, what is the probability of finding the electron anywhere between the two spheres? What does this mean? R is fixed, delta R is fixed, but the angles may change. We have two angles. One is theta, the other is phi. To find the total probability, regardless of what the orientation is, what is the rule? We add up the probabilities over the angles. So, we have, because angles are contained only in d tau 2, we have this expression, r square dr. This is d tau 1. Let us just write d tau 2. This expression, when we integrate this part over the angles, gives us the total probability of finding the electron anywhere between the two spheres in which the radii differ by just dr. But the value of this integral, what is it? This is a double integral. And the variables are angles. One is theta, the other is phi. All space for these two angles. This is 1. This is just normalization integral for the y functions. So this is 1. The net result is this factor, which is r square times r square times dr. So this is a probability distribution in R. The part, this factor, is denoted by another letter, P, and it is called the radial distribution function. All right, let us show the radial distribution function for several states. P for 1s R function. The 1s function is just normalization constant, which was 2. 2 times e to the minus r. All right. If you plot the graph of this function, it has no zeros. Remember, r goes from 0 to infinity. So this is R function, R1s. The radial function, the corresponding radial distribution function is P for 1s is R square times square of it, 4 times e to the minus 2r. Please note that this information is useful in making such plots. Number of nodes of, or number of zeros of P function, radial distribution function, is the same as number of zeros of the R function. Because let us say if a given R function has 4 zeros, 4 nodes, then R square will have the same number of zeros, isn't it? For the 1s function, as you see explicitly, this function doesn't have any nodes, and therefore its square is not going to have any nodes. However, because of this factor, R square, when we plot this function here, it will look like we know because of the R factors, small r, it is 0 at origin. It's always 0 at infinity, which means, and it's always positive, which means it has to pass through a maximum. And that you see here. All right.